Okay, so we're going to look, before we get specifically into how we can change to cylindrical coordinates, let's revisit coordinate changes in general. And in our last lesson, we looked at them in 2D. Now we're going to look at the 3D case, where now I have x is a function of u, v, and w. Same with y and z. So first we'll change the integrand, and then we will need the Jacobian, which is going to take into account the stretching or the shrinking of the region in the new coordinate system, and then we'll have some new bounds. The Jacobian extends really nicely to this 3D case. It just becomes this 3x3 determinant of this, or this determinant of this 3x3 matrix. So let's go to cylindrical coordinates and see how this plays out. We're going to write the Jacobian here in terms of r, theta, and z. And so I'm thinking of r up above as like the u that's shown in this, theta as like the v, and z is like the w. And so I'm going to find the determinant of this 3x3 matrix. And we'll just fill out what each of these become. Partial of x with respect to r. I'll just do this real quick. Okay, when we take this determinant, we're going to end up getting r cosine squared theta and minus, or actually plus, r sine squared theta plus 0. And just like last time, that's going to simplify to just give us r. So our Jacobian is actually the same as it was in polar. And we can see how this is going to make sense. Let's actually put it down here and then we'll look at the picture. So the Jacobian is r, and then we can decide what ordering we would like to integrate with respect to. So let's say we just did dz, dr, d theta. There's 6 possible orderings, right? So that part's optional, or this part can change. But let's see visually how this makes sense, why this would be our whole volume element. So up in this picture here, I want you to think of delta V as the volume of this. Oh, now it's this like polar rectangular box, right? And so I'm going to need the height, and we're going to call this height delta Z times the area of the base. But notice that we found the area of the base before, because that's exactly what we were doing in polar. So that's exactly the r delta theta, because that's just the polar rectangle from 12.3. And so we can simplify all of this, and this is going to tell us that delta V is, I'll just move around the order of them here, is going to be delta r, delta z, delta r, delta theta, which means that dv in my integrand becomes r, dz, dr, d theta, which is what we also get by just calculating the Jacobian. All right, and then we're going to also need to rewrite our integrand here in cylindrical coordinates. So I'm going to replace x with r cosine theta, y with r sine theta, and then z can just remain z. Okay, so let's talk through how we can evaluate this in a specific example. So we're going to do an example here in cylindrical coordinates, how we can find the volume of a region. And for this example, we're going to start with the ordering dz, dr, d theta. This is typically the ordering I try when I'm doing integrals in cylindrical, unless I'm told to do it a different way or unless this is too complicated. But this is usually my go-to starting ordering. So in this case, we need to sketch what this region looks like first. So take a moment, put it on pause, and see if you can sketch it. Okay, so the sketch you should have gotten was, this is a top cone here, and then we have the sphere of radius 3. So we actually are looking at just this kind of ice cream cone shape here, where they intersect. And to find the volume, since this is a three-dimensional object where the bottom of the object is not the xy plane, we're going to need a triple integral. Let's call this whole ice cream cone and the ice cream itself E. And to find the volume, we will just be adding up the little dv's everywhere inside. So my integrand's just dv. Now we need to set up our bounds. And yes, I am going to tell us to switch to cylindrical, not just because this is in the section on cylindrical coordinates, but because this is an object that's a great candidate for cylindrical coordinates. And here's what you're looking for. First, you look for objects that are symmetric about the z-axis, which this one is. And the other reason we know this is a good candidate for cylindrical is when I look at the shadow of this region on the xy plane, we can see it's going to be a circle. And so that's telling us cylindrical is the natural coordinate system because it's basically polar with z for my third coordinate. So go ahead and take a second and based on this, see if you can set up the bounds for this integral. Okay, so first, and you actually, I didn't quite specify which order I want you to do. Let's do the ordering dz dr d theta first. And that's usually my go-to ordering that I always use with cylindrical unless I'm instructed otherwise. So let's do that first. We can do the integrand, that's pretty quick. We showed that. And then let's give ourselves some space here. But the integrand dv in cylindrical turns into r, and then dz dr d theta. And let's start with our inside integral first. So let's start with the dz. We are going to shoot an arrow in the direction parallel to the z-axis, and we're going to look at where it enters the region and where it exits. And so you can see it's always entering on the bottom cone. Oops, this is going to be z. It's always entering on the bottom cone and exiting on the top cone. And so the bottom cone is z is square root of x squared plus y squared. Now when I'm doing this in cylindrical, I'd like to switch it to be not in terms of x and y, but in terms of r, z, and theta. And so let's look at that bound right here. We know that square root of x squared plus y squared is just r. So that's just this little piece here. That means it enters along just z is equal to r. And then the sphere of radius 3 centered at the origin, let's write the equation for that. So that's going to give me my top bound. So I have x squared plus y squared plus z squared is 9. I'm going to solve that for z, and that's going to be the positive square root of 9 minus x squared minus y squared, because it's just the top half of the sphere where this is exiting. And then in cylindrical, we can replace x squared plus y squared with r squared, so this just becomes 9 minus r squared. And that's going to be my upper bound here, square root of 9 minus r squared. And that's, I want to match these colors here so you can see what they relate to. So let's make them match. Okay. And now to figure out dr d theta, we're going to be looking at the shadow of the region on the xy plane. So the shadow is this circle r. And we want to see exactly what the radius of that circle is. And so I need to figure out what's causing the circle. And you can see the circle's coming from the intersection of the cone with the sphere. So let's find where they intersect. Okay, so the intersection, I would recommend you do it in cylindrical. So this is the intersection of the cone with the sphere. Z is square root of 9 minus r squared. We're going to set them equal to each other, and that's going to give me r is square root of 9 minus r squared, or r squared is 9 minus r squared, which I can get 2r squared is equal to 9, and then r is 3 over square root of 2. And that's going to be the radius of this circle. So let's sketch the shadow I'm talking about here. that's going to be this radius, u over square root of 2. Okay, so if I'm setting this up in, it's now polar, basically, I'm shooting an arrow radially outward, and I'm seeing that it's entering when r is 0, and it's exiting when little r is 3 over the square root of 2. And then my theta in this case, I'm just going to go all the way around the circle. So theta goes from 0 to 2 pi. And this is my setup now. And then we can just go through and integrate. So I'll put this on pause for you to finish the integration. And then you can check your answer. Okay, and here's the rest of the integral, and the main thing here was I did a u sub, and I actually just did it in my head, but you can write it out if you'd like, but that gets you to here, and then just some simplification from there. Now let's retry this problem using a different ordering. Let's try it if we were going to do the ordering dr dz d theta, and again, I would only use that ordering if we ask you to switch it, because in general it's going to be most straightforward to just do dz first. But my integrand is still going to become my Jacobian, so I still have the r coming down here, and then it's just this new ordering. What I would do with these is I would actually notice your theta in this case, because it's symmetric about the z-axis, and because your theta is your very last one you're using here. My theta is always going to be the constants. That's just how far around I've rotated. So that's fine. That's going to be the same in both. Now with this z and r, what I recommend doing is actually drawing a little slice of the zr plane if you're going to set it up with respect to r first. So let's do a little slice here. And I would always just do positive r, and I'm going to show you visually what we're doing. This is the z and this is the r plane. And what I'd like to do is just sketch what I have. So my picture, I'm going to have the bottom part of the cone, and then the top part that's coming from the sphere, and I'm just drawing the line there so you can see basically this region. Oh, let's not do that color. Basically showing you where that little cutoff occurs is that little line there. Okay. And so this is just the slice in the ZR plane. And so what I recommend is that you ignore the theta piece right now and just set up in the ZR plane what your bounds would be if this was just a double integral for z and r. Because then the idea is we're going to take this, multiply it by a tiny little width in theta, and rotate it all the way around. And you could actually use the same idea to set up your bounds with respect to z first. You'll notice we're going to get the same result if we had thought of it this way. But this is especially helpful if you're thinking of it with respect to r first. So just pretend you can, like, in your mind, pretend that you're covering up this last integral, and that you really just have a double integral and you're trying to set it up. Okay, so in that case, because I'm trying to integrate with respect to r first, I'm going to shoot an arrow radially outward. Oh, yes, radially outward in the r direction. But in my ZR picture, that's going to look like this, because this is the r direction. So I'm going to just shoot something radially outward in r, and I'm going to look at where it enters and where it exits the region. So that's equivalent to shooting out radially in the 3D picture. But okay, so it enters and exits. So notice it's entering and exiting in different spots depending on where I shoot. So if I shoot down here, let's start with that first. We'll call that, well, that'll be the first piece. It's entering when r is 0, and it's exiting along this line here, and that's the line that z is equal to r, because that's coming from the cone. So this line here is z is equal to r. Okay, so that's going to be my upper bound, rz, because that's where it's exiting. And then I look at what are the largest and smallest z values. And for just that purple part, z could be 0 or z could stop right here. And we need to figure out what that is. We saw over here that the intersection point was 3 over square root of 2. And since this is z is equal to r, that means my z is also 3 over square root of 2. So that will be my upper bound for z, just for that region. But now we notice, oh wait, we're going to need 2 double integrals because this whole first setup just worked for that purple part. And now, or excuse me, 2 triple integrals. And now I need to set it up. I need to take into account this part, like the actual ice cream part. And so let's go ahead and put it on pause and see if you can figure out what the integral will be for that part. Okay, so here we're shooting our arrow and we're shooting it parallel to the r axis, which in this case, here's my r axis. And we can see it's entering the region when r is equal to 0. And it's exiting, now not when z is equal to r, it's now exiting along that sphere. And the sphere in terms of r over here, let's rewrite that. Sphere, top sphere, z is square root of 9 minus r squared. So we're going to solve that for r. That means that z squared is equal to 9 minus r squared, and that means that r is positive square root of 9 minus z squared. And I'm just using the positive because my r can only be positive. We restrict r to stay positive so that we have a unique representation for each point. All right, so that's the top bound. And then z, my z bounds are just going to be the smallest and the largest z values where I could have shot this arrow. And so the smallest z is 3 over square root of 2 in this blue region. And the largest one's up here. This, let's see, was a sphere of radius 3. So the largest it could be is 3. And if we evaluate both of these and add them together, we'll get the total volume as well. So let's try another example.